Good evening, ladies and gentlemen. This is DMJ News. I'm your host, Dean Fias, and with me, as always, my co-host, Madeline Kondik. And today we have a story about spectroscopy, or the absorption of light by a colored liquid. Before we go to Jess, I need to explain the two basic concepts of spectroscopy. The first one being how a spectrometer works. A source sends a wave of electromagnetic radiation to a monochromator. This monochromator then selects and diffracts one particular energy or wavelength and sends it through a sample to a detector. The detector then reads and displays the absorption of the sample. Along with the basics of a spectrometer, you also need to know about Beer's law. Beer's law is a relationship of a light's absorbance of its solution and its concentration. Now we'll go to Jess Kondik, our field reporter, with our expert scientist.
Hello everyone, I'm here with Dr. Gordon Ramsay.
Hello, Jess.
Today he will be explaining to us the spectroscopy lab.
First off, in the lab I used a cuvette with DI water as a baseline. I set the spectrometer's transmittance to 0 and its wavelength to 340 nanometers. I then placed the water-filled cuvette into the spectrometer. Once in, the transmittance was set to 100. At that point, the absorbance should be 0. The next step is easy. I removed the DI water and placed a cuvette filled with 0.1 molar copper 2 sulfate into the spectrometer. I closed the lid and recorded the absorbance of the solution. All I did from there is the same exact steps, only changing wavelengths increasing by increments of 20 nanometers. I set the spectrometer to 0 transmittance, put the water in, set it to 100 transmittance, made sure at that point the absorbance was 0, and then placed the water cuvette with the copper 2 sulfate solution cuvette to record the absorbance. I did this each time with different wavelengths until a wavelength of 900 nanometers. The next step in the lab was finding the concentration of a solution. I prepared 5 different cuvettes of copper 2 sulfate solutions, each containing 10 milliliters of 0.02 molar, 0.04 molar, 0.06 molar, 0.08 molar, and 0.1 molar copper 2 sulfate solution. I used the wavelength that produced the max absorbance from the first part of the lab throughout this part, which was 820 nanometers. Using this wavelength, I measured the absorbance of all 6 solutions, recorded the absorbances, and made a graph with the absorbances of the 5 solutions with known concentrations. Using this graph, I was able to determine the unknown concentration of the solution with the known absorbance. Thank you, Jess, and back to DMJ News.
Thank you, Jess and Dr. Gordon. Now my co-host Maddie here has the results of the experiment. Maddie?
The equation M1V1 equals M2V2 was used to determine the volume needed to dilute a 0.1 molar solution of copper sulfate into 4 other solutions with molarities of 0.08, 0.06, 0.04, and 0.02. With different concentrations and a constant max wavelength of 820 nanometers, absorbances recorded were placed into a graph. When the graph is linear, it is an accurate representation of Beer's law, or the relationship between the absorbance and concentration. In Dr. Gordon's experiment, his R squared value was 0.984, and the closer to 1 an R squared value is, the stronger the linear correlation. Another adherence to Beer's law is 0 as a y-intercept. The experiment yielded 1 of 0.063, allowing the experiment to be valid in finding the unknown concentration. Knowing Beer's law is valid, the absorbance found from the unknown concentration can be plugged into the linear equation to find the molarity or concentration of the solution. In Dr. Gordon's experiment, his absorbance of 0.840 yielded a concentration of 0.053 molar.
Thank you, Maddie. That's all for our spectroscopy segment today. Next, we're going to be going to Jack Colvig with the weather.